Okay. Thank you, everybody, for joining us today. We are really excited to announce the Ultium Motion system and share with you some of the details, as well as some examples of it in action. For those of you who are joining us for your first webinar with Noraxon, welcome. And I'll go over a couple things here before we kick it off. We will have a question and answer section at the end of the presentation, so please feel free to type in any questions into the Q&A section or into the chat box on Zoom. We will get to those at the end. And of course, you know, what I'd like to start with is just talking about, some of the advantages and the challenges related to inertial motion capture. Obviously, the Ultium Motion is our second generation inertial motion capture system. So some of you may be familiar with our Research Pro systems or our clinical IMU systems. And so to kick it off, I just want to touch on some of those advantages of why inertial motion capture makes sense for a lot of people to utilize for looking at kinematics and biomechanics. So of course, a big one is its portability factor. So given that it's a wearable system, you have the ability to take this system out into field scenarios, as well as use it in various different lab spaces or clinic spaces, and not have to really fuss around with too much of a setup. Of course, you just have to apply the sensors onto the subject and make sure that they're generally within the measurement range, and that's it. And you can capture data. Another advantage, of course, is its ease of use. So if we look at this compared to a traditional motion capture system, again, describing that workflow of just having to essentially place sensors on the body, perform a quick calibration, and then you're able to stream in that live kinematic data and start to use it. And then we have direct measurement. And so this is really, looking at the differences between inertial motion capture and some of the new forms of motion capture that are coming out, where we're looking at markerless motion capture, for instance. Those are using computer vision techniques, and it's not actually taking any measurements of the individual, but rather doing image processing to make estimations. They have shown to work really well, but then there's also chances that they could mischaracterize certain movements. And what inertial systems allow for is that direct measurement of the rotation, of the acceleration of that particular body segment. We can take that directly measured data and then we turn it into the kinematic data by putting it through some various processing pipelines. It's those direct measurements that allow it to achieve accuracy levels that are, close to the traditional optical motion capture systems that might use marker sets, for instance. And also, it gives us an ability to actually look at certain parameters that even some of the optical systems can't necessarily measure that well, with respects to internal and external rotation, or immediately measuring rotational velocities or the impact accelerations that are actually occurring. When we look at it with reference to those other systems, again, they're just looking at how something is traveling inside of a known volume and then applying math to get to the rotational velocity or get to the acceleration. With an inertial system, you of course are measuring those data points, and so you can use those to your advantage depending on whatever application that you might be working with. Now, that isn't to say that it's a perfect system. There, of course, are some challenges, and with these challenges, this is something that we at Noraxon are trying to tackle each and every day as we continue with our development and our innovation over here. So with the Ultium Motion system, that was something that we really wanted to address as some of the top challenges that are experienced by users when an inertial motion capture system is in operation. So of course, the biggest one, and many of you I'm sure have dealt with this, is with reference to magnetic interference. So given that the inertial sensors do rely on a magnetometer as one of their data inputs, any ferrous object, anything that has a magnetic field, be it passive or active magnetic field, can start to interfere with that magnetometer's data and skew it over time, cause some drift. And so that has traditionally been a challenge with inertial motion capture systems, and you know, us along with other companies in the market are constantly, you know, working on different ways to handle that, and you know, have created some sophisticated techniques to be able to manage that magnetic interference. And of course, you know, what we wanted to address with this system is you know, how do we handle that better at the sensor level, and then what can we do from the software side to manage that experience better as well. Next is going to be high impacts and velocity. So the inertial motion capture systems up to this point have really only been able to capture data that is, let's call it, you know, within normal ranges of human movement. So that would be things like walking, you know, general range of motion tasks or daily activities of living. But what we found over the time that we've had our myomotion systems on the marketplace, which has been about 8 years now, is that people have consistently, you know, taken that advantage of the portability, for instance, and brought it into these field situations where now they're looking at high performance. They're looking at really high impacts, high velocities in various different movements, be it sprinting or, you know, rotational sports, or, you know, any other forms of dynamic movement. And the previous systems, given their limitations, have not necessarily been able to keep up in certain situations. And that was a challenge. We would try to manage that as best we could using software techniques and see what we could do there. But at the end of the day, it was really the range, the sensor itself, that was causing that issue in those situations. And then next, as far as challenges are concerned, is sensor displacement. So describing this, of course, given that it's a wearable system, and you can see here in the picture that we've got these sensors strapped onto the individual, after we perform our calibration, if those sensors move and the body doesn't actually move, that's going to have an effect on the information that you get or the outputs that you receive afterwards. So sensor displacement is kind of a twofold challenge, because it can be caused by a few different things. That can be not only just how the sensors are fixed to the subject, so what kind of strapping mechanism is being utilized, but then also, is the sensor large? Does it have a lot of inertia that it's going to, you know, when it receives high impacts or velocities, is it going to move just based off of its size and its weight? So with these three challenges in mind, that's what, again, we really wanted to focus on as we created the Ultium Motion system. And so I'd like to, you know, go over some of those feature sets that help us address those challenges. So of course, these are our key features, and I'm going to break these down one by one as we go through the presentation today. And so, of course, you know, one is just the state-of-the-art sensor design. So providing the ability to achieve measurement ranges that have not been seen before with an inertial motion capture system. Similarly, you know, on an internal level, providing high sample rates. So taking more data as we, for measurements that are going to provide us with less error and more data to utilize to fill into our fusion algorithms that we're using to provide that kinematic data. Small form factor, so making the sensors smaller, lighter, so that we don't have to address some of that sensor displacement issues that we might have seen previously. And then, of course, the universal connectivity, and I'll get into this in more detail, but this, you know, really actually plays on more of an advantage of the system and allowing that ease of use to really take hold and be something that can be promoted when you've got multiple devices that might be in operation within the Noraxon platform. So let's break this down. So if we talk about that state-of-the-art sensor design, so in this case, what we're looking at is a baseball pitch. And you'll see here in the second video with the Research Pro system that when we get to that release point, the model completely breaks down. This was not something that we were able to achieve with the Research Pro system simply because those measurement ranges were not adequate. We can see it here in the data stream down below that when we approach that 1600 G mark for the hand acceleration, which is basically occurring right at that release point, right when that whip-like effect occurs, it completely flatlines. It's not even able to take any more data up to that point. And so you can do some tricks where maybe you do some interpolation and you try to estimate what that peak will be. And maybe you can fix what the model looks like to make it pretty. But at the end of the day, if the data that's providing the inputs for this output here are not sound and solid, then you're not going to have good information to utilize to make any decisions, to perform your research. So if we look at the other side now, and something pretty glaring that I always like to bring up is if we just look at the scales. In this particular case, we can see here that this is topping out, you know, the upper end here is 17 Gs, where the upper end here is 80 Gs. And you can see that as we go through this motion, we're seeing that hand acceleration peak out at almost 70 Gs of acceleration. And we're actually able to measure that with this system. We can see that full waveform all the way up to the peak. We're getting a smooth motion as we go through the throw here. And of course, that's then influencing what we're seeing on the avatar model. So it's pretty interesting to see how much data we are actually missing with the previous system when it came to, you know, high velocity movements such as this. Going from a 16G measurement range to a 200G measurement range is really allowing us to break that barrier into these high performance activities. In addition to that 200 Gs, we're also able to capture rotational velocities up to 7,000 degrees per second, whereas the previous system, the Research Pro system, could only capture up to 2,000 degrees per second. So that's over 3 times as much data that we can capture with this system, and then definitely, you know, approaching those upper limits of human movement. So next key feature would be that high sample rate. And what this provides us is the ability to actually have more data to utilize when we push it through our filters. That starts on the internal level. And with the Ultium Motion system, we're capturing data internally at 1600 hertz. If you compare that to the Research Pro system, that was only at 800 hertz. So with the new sensor, we're actually capturing data internally 2 times faster, and that's influencing our outputs and giving us the ability to output kinematic data at 400 hertz. This is the highest sample rate that's available for a inertial motion capture system on the market right now, as far as kinematic outputs are concerned. We're already fairly high with the Research Pro system, allowing up to 200 hertz of kinematic outputs with a full body system. But now giving the ability to achieve even higher, with 200 being the low end and 400 being the high end, you can see that you'll be able to have better representation of those true analog movements that are occurring. So that, coupled with the high measurement ranges, is just providing us with better data to utilize to create more accurate representation of these movements, especially when we get into, you know, various different situations, whether it be slow movements or even those high impact, high velocity movements. Next is going to be the size reduction. So you can see here that we've reduced the size in 15% in the length and width, over 30% in height, and over 50% in weight. So the sensor has become smaller, which is allowing us to have better experience when it comes to potential sensor displacement issues. You can see here that, of course, the length and width are reduced looking at the system, but then the actual piece that really makes a difference when it comes to that inertia and that displacement is that thickness. So there's not as much of a moment arm on this sensor that when you're moving around, you could see the sensor move or fly out or anything like that. The neat thing about this is even though we achieved a smaller size sensor, we're actually able to improve the overall operational battery life. So this sensor had an 8-hour operational battery life, whereas the Ultium Motion sensor, we're able to achieve 10 hours and sometimes even greater than 10 hours, depending on the sample rate that's being utilized. So with a size reduction, we were actually able to increase the operational time, which is really awesome. And that's actually because of the efficiency that's built onto the motherboard of the sensor. So how that electronics design was handled such that it didn't need to waste power in certain areas. Of course, when we talk about a size reduction and how that affects sensor displacement, I have to also mention the strapping system. So we launched our new straps for the motion systems this past year. And so we're taking that same concept, but we have clips that are now utilized that snap into the sensors. And you can see here the little grooves that those hold into. And they do a great job of making sure that that sensor stays in place on the strap. And then it's just up to you to make sure that you strap down tight enough on that limb such that it doesn't move up or down or rotate around on the particular limb that you might be capturing. So next, and this is a really neat feature and something that we've been aiming for is, when we first launched the Ultium EMG system in 2018. And so this is a setup, now that we have the Ultium Motion system, we have a completely universal system. And in fact, the actual sensor charger can be used with either sensor. So it's fit so that the same charger can charge EMG sensors or motion sensors. And be it that they use the same communication protocols, they can also communicate with the same receiver. And so you can actually mix and match up to 16 Ultium sensors, EMG or motion, with a single Ultium receiver. Of course, you have the ability to combine two receivers if you want to increase that and perhaps do full body motion capture along with 16 channels of EMG or any of the various smart leads that we have available as well. But this universal connectivity is something that is not necessarily seen around the marketplace and really plays into the ease of use advantage that we have with the system, because now you've got a smaller footprint with the Ultium system, the receiver on your desk, and you can connect up to whatever sensors that you'd like to measure. And so you can play around with those configurations depending on the needs of your given application. That's also going to be a more economical approach for some people who don't necessarily need 16 EMG sensors or full body motion capture, but instead maybe a smaller subset of sensors, let's say 7 motion sensors for lower body motion capture, and 4 to 6 EMG sensors to look at the muscle activation patterns, let's call it, during running analysis or a walking analysis. Now you can just have a singular system that communicates with both those sensors, and you don't have to purchase multiple units to be able to achieve that. So again, I just want to review some of these key technical specifications of where we've made these advantages. So first, of course, are those measurement ranges. So seeing the 200G and the plus or minus 7,000 degrees per second allows us to achieve those measurements in the high velocity or high impact situations. If we compare that to the previous system, to Research Pro, again, for acceleration, we were only able to capture plus or minus 16G. In that first video that we looked at, we were able to see what the effect had on that when we got to those upper ranges. And then next we have the angular velocity at 7,000 degrees per second compared to the Research Pro at 2,000 degrees per second. We have that 3 times increase for the capture of the angular velocity. And then we have an improved magnetometer as well, so giving us a higher magnetic range to be able to measure and see how that might be influencing our data. But the key thing here is if we look at these measurement ranges, there are no other motion capture systems, inertial motion capture systems on the marketplace that are able to achieve this here. And so we're really proud that we were able to build this into a sensor and start to utilize it. And of course, really excited to announce it to everybody today. Next is going to be those internal sampling rates. So again, at 1600 hertz for acceleration and angular velocity, that's going to be twice as much as the internal sampling rate compared to the previous system. So giving us 2 times more data to be able to utilize when we push that through our Kalman fusion algorithms. We've got the ability to log up to 8 hours or 8+ hours of data on each individual sensor. And with the inclusion into the Ultium system, we actually have the ability to not only do online recovery, which was possible with the previous motion system, the Research Pro system, but now we have the ability to do offline recovery, which is similar to how the Ultium EMG system is able to function. So with the sensors plugged into the charger here, this charger, when it's connected to the receiver, you can actually pull data from the sensors and have it fill in the gaps of certain recordings. And so I'll show you an example of one that we did previously where we basically utilize these in full data logger mode. But if there's ever any losses of data, whether it be you're going outside of the transmission range or longer interruptions for whatever reason, you'll be able to pause that online recovery and then utilize the offline recovery to pull all of the data at the end of your day so that you don't have to sit there and wait for the online recovery to take place wirelessly. The battery, so the operational runtime, again, I mentioned that even though we have the smaller sensor, we were still able to achieve a greater battery life due to the efficiency of the board design. So then we move on to the sensor weight. So I had mentioned that we achieved a 50% reduction, but here's the actual spec on that. Of course, the Ultium receiver has that universal connectivity, so being able to capture data from up to 16 channels of Ultium EMG or motion sensors. And then, of course, we've got the universal sensor charger, which is able to hold up to 9 Ultium EMG or motion sensors. So you can mix and match those within the charger station as well. And then finally, if we look at our measurement outputs, so these are going to be what you're going to see on the back end with regards to the anatomical joint angles or the orientation angles. But then you can also see that if we look at even the raw data, those can be captured or presented rather at 400 hertz for acceleration and angular velocity, and then 100 hertz for the magnetic field and the quaternion data. So now let's talk about some applications. So of course, inertial motion systems the goal of them is to measure kinematics, measure human movement, look at changes in motion patterns through various different situations. On the research side of things, that would include general motion analysis, rehabilitation engineering, the utilization of inertial system in real time during a teaching course to describe or demonstrate a certain application of movement. Maybe it's gait or another type of coordinated movement. On the clinical side of things, of course, we've got gait analysis, balance testing, general range of motion testing. For ergonomics, we're looking at the work safety parameters, human factors, and engineering and product design. So the ability to look at how individuals are interacting with a given workspace or a product, or in this case, as you can see in the picture, a chair, for instance. And so these categories here were fairly well served by the previous system, and so we can play off of the advantages and the benefits of the inertial motion capture system, even the Research Pro systems, within these three categories. Where we really improved upon with the new sensor, not only providing more accurate data for these three categories, but now if we go into the sports side of things and we start to look at that high performance testing, the return to play analysis, the throwing, striking, running analysis, those are being served much better with the Ultium Motion system because of that ability to achieve those higher measurement ranges. As we demonstrated previously, these types of analyses, looking at throwing, for instance, was more or less not feasible with the previous system. In addition to that, things like sprinting, stuff where there's really heavy impacts that are compounded one after the other, was a challenge as well with the previous system. So while we enhanced these application areas, we've now broken into a new barrier or broken through a barrier in the sports and the performance side of things with the Ultium Motion system. So the package, so this is what the system package will ultimately look like. So of course you'll have an Ultium receiver that's going to communicate with whatever number of Ultium Motion sensors or Ultium EMG sensors that you might have. You've got the Ultium sensor charger, a strap set, which we've got various different options, as well as a la carte items if needed. A travel case, so the ability to pack everything up and travel or transport the system safely. Accessories such as sensor tape, and then of course, the cables that would all come connected or come to connect the system and the charger to the receiver, for instance. So it's a fairly compact system, and this plays into the small footprint that the system has overall. It really is truly portable. The Ultium Motion receiver is powered by USB, so that USB cable is providing data transfer and power. So you can bring that outside with a laptop, for instance, and you'll have full connectivity and ability to use that with the motion or the EMG sensors. And then, if we talk about the strapping system again real quick, so one of the things I didn't mention, but would be the silicone beading on the backsides of the straps that really help achieve good hold onto the skin, so that those straps don't slip and that you don't see that sensor displacement that we were discussing. So this is the general package here, and then of course this can be augmented with various different sensors, be it EMG sensors or smart leads, whatever is necessary for the given application. And some of you may be portable lab customers, and those of you might be looking for a portable lab. So the Ultium portable lab will be shipping in Q2, so sometime this spring. What this will include is a fully Ultium integrated portable lab system where you can achieve up to full body motion capture with 16 Ultium motion sensors and up to 16 Ultium EMG sensors, as well as the integration of up to 2 of our 9-ox cameras, all self-contained inside of the case here. Everything's built in. It creates a super efficient way of utilizing these instruments in the field and giving you the ability to just wheel this around, take it where you need to go, open it up, connect the 2 USB cables to the computer, and then you're ready to go. And so we're really excited to finally get to this this next level of the portable lab system. For those of you who have been following, this will be our I believe, our third iteration of the portable lab, not counting some, very, very early prototypes that we had for a little bit, maybe 5 or 6 years ago. So be on the lookout for this system, and we'll of course be doing further announcements as this starts to come live. So we talked about the hardware, so now let's talk about the software side of things. So what are some of the aspects, what's provided with the system? And really not much has changed as far as what data is provided if you compare it to the previous Research Pro system. Of course, you get the ability to achieve those higher levels of measurement. You get more accurate data, less error with the the increases in sample rates and everything there. But what we're really ultimately ended up doing here is we're capturing 3D kinematics, accelerations, and joint trajectories. And the idea is that we want to measure changes in movement patterns. Those can be looked at, utilizing this data that we have here. Of course, we have our anatomical joint angles, orientation angles. So that's how each sensor is rotating in 3D space outside of the body model. We can look at linear acceleration profiles for each one of the sensors. We have several joint trajectories that can be looked at, even a center of mass trajectory, whether it be in a relative context or actually looking at that translating over a given area, which we'll see a couple examples of here shortly. We have the ability to define contacts. So during walking or running or even jumping, we can see when the feet are on and off the ground. And utilize that to segment data for analyses, let's say a running or a gait analysis, for instance. We have the ability to generate user-defined angles, so we can take the rotations of one sensor and we can compare that to another sensor and create a user-defined angle that might look at the difference between those two. And then, of course, we have our raw data that's available at the quaternion level, or the raw component data, so looking at the acceleration, the rotational velocity, or the magnetic field data. And so these are all going to be enhanced by further software developments, which, of course, the Ultium Motion system will be coupled with a new version of Milo Research. And so some of those additional tools include updated filter designs and options for enhanced optimization and stabilization of the data, enhanced magnetic field rejection algorithms, both on the software side and also, the inclusion of some of those or some of the functional calibrations, which we released in the 3.16 version this past year. So utilizing those, the functional calibration, as well as the additional stabilization tools that we've got, you'll be able to use the system in magnetically affected areas without issue. Of course, we have multiple calibration options, not only the standard calibration, which has a couple different positions that you can choose from, whether it be the standard soldier pose or a seated calibration. But then we have our functional calibrations for use in those magnetic environments. And we also have our calibration adjustment tool, which we'll be aiming to have integrated with the Ultium Motion system in the near future here. Of course, we have our various different viewer tools that are available. So whether that's enabling those joint trajectories to look at the movement patterns of a specific joint, or looking at different viewpoints of the avatar. And we're aiming to have some additional viewer tools that will be available, as well as some options for different avatars as well. So keep an eye out, because we'll be basically unveiling these additional tools as we go forward through the release plan of the Ultium Motion system. And so we'll be posting those up to our social media and to our website. So keep an eye out and make sure you go and follow us there to follow along. So one of the things that I want to talk about real quick is those optimization filters, or the stabilization filters. And so this was a really neat measurement, test measurement that we just did the other week, where we actually were sort of stressing the system out as much as we could. And so we went on a 2-hour hike in Arizona. It was a beautiful day. For those of you that haven't been to Arizona in the winter time, it's probably like summertime for most other places in the world, but it's generally cool and sunny, and so it's a great time to get outside. So we went on this 2-hour hike, and basically what we did is we set up the system in the parking lot of the trailhead. We started the measurement, did the calibration, and then went about the hike, and then finished that measurement at the same spot. The goal here was to be able to measure what the error, the displacement, overall displacement error was from the start and the finish. We also utilized a GPS and implemented that data into MR3 so that we could see the actual track or pathway of the hike and have that be compared to the pathway generated simply by the joint trajectories with the motion system. So with our standard filter, and this would be just utilizing some of the benefits of the new system, like the high sampling rate, and having the recording and doing some forward and backward optimization, we were able to see a 2.5% error. So compared to the total distance of the hike, which is about 7 kilometers, we only saw a 183 meter difference between the starting and the ending positions after that hike was complete. And I guess I didn't necessarily mention, but we were using this in full data log mode. So there was over 99% loss of data by the time that we finished. And we were able to use that sensor charger to pull all the information from those sensors and fill it into the recording so that we had a complete recording without any data loss issues. So not only, were we stressing it in that way, but then of course with the hike, you've got various elevation changes, you've got, multiple impacts that are occurring depending on if you're going uphill or downhill or, turning a corner. And so we were very excited to see that we had this amount of error just with the standard filter option. Now, if we apply our optimized filter, you can see here just in general how that pathway starts to look more and more like the GPS pathway that we are seeing up here. So we, lose some of that variability that you're seeing in this area through the optimization, and really all that this is adding is just some drift corrections that are part of this optimizer filter profile. And of course, we'll have more details on both of these available. As time goes on, we'll be, creating documentation so that everybody has an understanding of what exactly is going on there. But what we were able to achieve here was a 1.5% error, so only 110 meter difference between the start and end positions. So those are very exciting results, especially after a 2-hour measurement. Neat thing is, in much shorter measurements, which are generally a little bit more common than 2-hour measurements, we're able to see errors that are less than 0.5% when it comes to the measurement of translation, and that's just because of not only the better data that we're utilizing with the system, but then also the updated enhanced filtering options that we're able to have access to because of that better data coming from the Ultium Motion system. So let's take a look at a couple of video examples here. So this is a full body baseball pitch. And I always like to try and stop this here if I can, right on that peak value. But we're able to see that at that release point, for one, you can see that we've got a really smooth trajectory of the hand motion here and the arm all the way through the pitch. But this is what I wanted to call out was the raw data. So this is the right hand. And not only, as we saw previously with respect to the acceleration signals, where we were seeing, about 70 Gs of acceleration as our peak value, but then we can also see the gyroscope signal with that peak value nearing, roughly 6,000 degrees per second. So with the previous system, only being able to capture 16 Gs of acceleration and 2,000 degrees per second of rotation, this type of movement was not possible to be able to capture. So we're very excited to be able to finally measure these applications and provide a solution to people who want to use wearable systems in these contexts. So now if we look at a soccer kick here, so an actual impact, where we're kicking a ball. And again, not only are we just having really smooth movements, the ability to capture that smooth leg trajectory here, but we can even see at that impact, and let's see if I can stop it on the peak again. Oh, I was close. Let me get back here. Oh, it's going crazy. Let me get back to that slide. Here we go. So we'll try and stop it one more time, see if I can get it right on that peak. Oh, okay. So what we're seeing though is roughly almost 100 Gs of acceleration. And that, again, was not something that was possible based off of the previous system. And so we're able to now capture that information, and we can see those impacts, whereas previously it just wasn't going to be feasible. It would cause error in the model. It would cause error in the data that you're seeing, which not only has an effect on just the raw information, but then the kinematics that are presented thereafter. So in this case, we've got a sprinting trial, and again, I wanted to pull out some of the peaks that we're seeing here on the feet for the acceleration. And so this is something where we can even just see that our ranges, our peak ranges, are around that 75 G mark. So again, with plus or minus 16 Gs, those impacts, maybe we were clipping them at 16 G, but as they compounded, and we weren't able to get back to those the measurement ranges because the impacts during sprinting are happening so quickly, that would ultimately cause some issues. And so now with the sprinting and the Ultium Motion system, we have the ability to capture this information and have a nice smooth representation of that sprint form. And of course, you can even see here that we have the Ultium Motion the Ultium insoles implemented into this measurement as well, so that we can get information about the pressure distribution, about the step timing, along with the kinematic data. So that would be another advantage of having that multi-device system. In this example, what I want to showcase is that ability to make those trajectory measurements. And so this is all, goes hand in hand with not only the sensor design and its ability to give us that better data with the high sampling rates, but then also what we're working on from the software side, the ability to enhance that contact detection, have better representation of the trajectories utilizing the acceleration data. And something like this, we weren't necessarily able to do. We can now capture backwards running, we can do sidestepping, we can see that change of movement. And again, that overall error that we were seeing from the start and end positions was less than 1%, even in this particular dynamic context where there's a lot going on, changing directions, heavy impacts, different styles of movement. And then finally, I just want to show a setup that is that multi-device setup. So again, being able to utilize the advantage of that universal connectivity and have a system that has motion, EMG, pressure distribution, all operating off of one receiver. And so in this case, this would be a great package, for instance, to be able to utilize for running or gait analysis, where we've got the lower body and the trunk for the motion capture. So we can look at the kinematics during those movements. We've got 4 channels of EMG to look at the muscle firing patterns as it relates to those movements. And then we have the Ultium insoles implemented as well to look at that pressure distribution, look at the contact patterns when somebody is walking or running. And all of these sensors, so those combined, so you have one for each insole. You've got 9 sensors for the for the motion system, and then 4 EMG sensors. That's 15 sensors. So that all communicates with one single Ultium receiver. So again, allowing that universal connectivity to take place and allow you as the user to craft your systems in a more economical way, so that you can have what you need without having to have multiple systems or purchase multiple systems. So we're nearing the end here, and I do want to just talk about the launch promotion that we're having, which will be taking place through the end of September, as you can see here. And so there's 2 options. So we've got new customers. So those are customers that do not have an Ultium Motion system. This promotion allows them to receive 1 free sensor and 1 full body strap set with their purchase of a minimum of 6 motion sensors. And then we have our current customers. So those are customers that already have a Research Pro or a clinical IMU system. And if they decide that they want to also purchase the Ultium Motion system, again, a minimum of 6 sensors as well as the Ultium receiver, they would receive a 15% discount on that system and a 1-year software maintenance contract for free as well. So 2 promotions to hopefully motivate everybody out there to contact us and learn some more about the system and potentially see if we can get it involved in your applications. Whether that be in the lab or the clinic or the performance center, to be able to utilize this equipment.